Alright, so now let's start with FRQ number 8. This is where it starts to get a little tricky. We have to start using information from previous units and stuff. Alright, so, I don't know why that's there. That's weird. Anyway, it says an astronaut who weighs 157 kilograms is floating in space at 6.3 meters per second. And so it gives us a diagram. So he goes this way at 6.3 meters per second. Alright, and he fires a thrust from his jetpack at 200 newtons for 2.4 seconds at a 75-degree angle. That's represented right here, to his direction of travel, as shown in the diagram. And so, to kind of make this easier to see, you have a circle right here, which is going to be the person, and he's going at 75 degrees. He's going over here, 6.3 meters per second. And let's just say the jetpack propels him upwards. Alright, and then this is 200 newtons for 2.4 seconds. That is the information that we're given. So in order to solve this problem, we need to set up a couple triangles. The first looks like this. Like that. Alright, so this is his final momentum. So what I basically drew here, alright, is he's initially going this way. He's going to the right. He's chilling. He's going along to the right at the first momentum. And then he gets a force upwards, diagonally at a 75-degree angle. Right here. At a 75-degree angle from his jetpack. His jetpack goes off and he changes direction and he goes this way. And so if you add the two vectors together, he goes in this final momentum. So that's our first triangle. Our second triangle is right here. Let's just draw it right here. It's what happens if you combine, because this is a force vector, right? So we can split this triangle up and further. So we could say this is the x direction and this is the y direction. We could say this is fx and this is the force in the y direction. So we're splitting this up. And so when you combine all these vectors together, what you'll get is this. So you get P2. You get P1. This is straight from this past triangle. But now we're going to do plus the force in the x direction. And then this will be the force in the y direction. And you see where I got that from? It's basically I took this triangle and I combined them together. I combined the forces together and I get this triangle right here. P1, P2. Okay? And so for formulas, all you really need to know, you don't really need to know any formulas. We're just going to derive them from these triangles. So now let's go to step 3. I'm going to write two things down here, and then I'll explain them afterwards. So you have F times T X equals F times T cosine theta. And then F times T of y equals F times T sine theta. Alright, so you might be asking, how did I get that? So the way I got this is, if you look at this diagonal right here, we can write this as F times T. Because what's happening is that he's firing his jetpack for 200 newtons for 2.4 seconds. Force, time. And so since this vector right here, let me reset, represents his jetpack firing off, since that represents it, the hypotenuse can be written as force times time because that is the jetpack. The jetpack firing is 200 newtons for 2.4 seconds. And so then so we have f of t of x, right? And so to get that we say that equals f times t cosine theta. And that's because it's in the x direction, we're doing cosine, right? Because adjacent, right, f of x over the hypotenuse. So we get ft cosine theta. For f of t of y, we do the same thing. This can be written as f of t, and so we do sine 75, or sine the angle, and that's going to be so opposite f of y over the hypotenuse. And so that's how you get these two formulas over here. And so then what you do is you go to the second triangle over here, triangle number 2. What this triangle says, all right, it basically says, okay, so what we'll do is basically what we have right here is just setting up for problems 8 and 9. We don't need this part until problem number 9, but it's going to be useful to have. We do need these two triangles though. We're going to need triangle number 1 and triangle number 2. And so for this problem, it's asking his new speed. So the way you find that is we use this triangle over here, and we simply use the Pythagorean theorem. So I'll write this over here. All right, more step 3. It's that P2 squared is equal to square root of P1, right, plus f times x in the x direction squared, or f times t, I mean, t plus times t the y direction squared. Actually, yeah, I got ahead of myself there. Since we're already squaring it, we will not need the squares right here. So P2 is equal to this, because P2 squared would equal to this squared plus this squared over here. And if we square root both sides, we'll get P2 is equal to this over here. And so if we plug in values, the values we're given, we'll get that. Well, first let's get our velocity before we get ahead of ourselves. P1 is equal to his initial mass times his initial velocity. And that would be 157 times 6.3. And you get his initial momentum is equal to 989.1. So now you have enough information to solve this equation that we've made at the bottom. Alright, so you can do this by yourself. For momentum, you're going to want to plug in 989.1. For f times t of x, we already have that derived over here. So it would be 200 times t times cosine 75. And then that entire thing is squared. Plus f times t of y, which would be f times t sine 75 again. And all that squared. And then you're going to want to add those two together. And then square root the entire thing. And from that, we will get that P2 is equal to something around 1218 as your momentum. Alright, 1218. So that would be newtons times meters. Right. And so, but we don't have our answer yet. We have the momentum, but we don't have his speed. To find that, we're going to have to go back to our original momentum formula, which is P is equal to mv. Alright? So when he was moving along, his velocity changed, but his mass didn't change. He didn't get any heavier. So we can say that 1218 is equal to his original mass times his new velocity, is Vf. So if you divide the two, you get 1218 by 157. You get 7.76 meters per second. And that is how fast he is going. And does this make sense? Yeah, it does make sense, because what he's doing is he's getting a thrust, so he's going to go faster than he did before. And yeah, that's how you do FRQ number 8.